Alright, here we look at a BJT switch example, and this type of circuit is often referred to as a driver, and I'll mention where that name comes from later on in this video. But first, let's do an ideal analysis for both V-in values, the value where the base 2 emitter is reverse bias, and the value where the base emitter is forward bias. Okay, so we're going to use 5 volts again for V-in for the forward bias value like we did in the general example. Okay, so here's our BJT. We've got a base resistor of 8.8K, a collector resistor 100 ohms, solenoid. And for those of you that don't know what a solenoid is, it's just an inductor that when you energize it, a rod of that solenoid will move, and often solenoids are used in, say, vending machines, where if the person puts in the right amount of money, the solenoid is activated and this rod of the solenoid will move and it trips a lever which opens a door and your soda comes out. Of course, if the solenoid's not energized, then the rod doesn't move and the door doesn't open and you don't get your soda. So that's just one example of where a solenoid is used, but solenoids are used in all kinds of various applications. So we have this solenoid connected to the collector resistor of the BJT along with the source voltage, as you can see on the right side, of 12 volts. So now also on the data spec of the BJT, or excuse me, on the spec sheet or data sheet of the BJT is the beta spec value of 300. So let's go ahead and look at the ideal case when Vn is equal to 0. Well, when Vn is equal to 0, this base 2 emitter like we have here is reverse bias, so no base current is going to flow ideally. And if your base current is 0, that means your collector current of the BJT is going to be ideally 0. So that means there's no current flowing through the solenoid, so the solenoid is not going to be energized, and it's going to essentially be off. So again, in the example, the vending machine, you would not get the soda because the door would not be tripped by the solenoid and therefore it wouldn't open. So here the solenoid is just de-energized because your collector current is 0. So de-energy, de-energized. And essentially your collector to emitter, like we talked about in the previous video, your collector to emitter is acting like an open. Okay, because no collector current means that there's no voltage drop across either the solenoid or the collector resistor, so this entire 12 volts would be across your collector to emitter, and since there's no current, that's the same current voltage relationship as an open has. Alright, now when Vn is the other amount which forward biases the base to emitter, well, now you do have a base current, and that base current is just going to be the Vn amount, 5 volts, minus the voltage drop base to emitter, which we're going to assume the transistor silicon, so minus the 0.6 volts, and then divided by the RB value, which is 8.8K ohms. Okay, so this comes out to 4.4 volts divided by 8.8K ohms, which is half a milliamp. Okay, now to get the collector current, we would just do a KVL equation and solve for IC. See, now since there's a base current, there's going to be a collector current flowing just like this. That's the path for collector current. So you see it's just going to be VCC divided by RC plus the resistance of the solenoid. So for analysis purposes, you're just treating this solenoid as a 20 ohm resistor. Okay, if instead of a solenoid you had, say, a LED in this part of the circuit, well, then you would just treat the LED as a voltage source of value, whatever the drop across the forward bias drop across the LED was equal to. Okay, so Here you're just going to have VCC, which is 12 volts, divided by a total of 120 ohms. And that comes out to 1/10 of an amp, okay, which is the same as 100 milliamps. Okay, so you see 100 milliamps is flowing through the solenoid as well as through RC and also collector to emitter of the BJT. So here your solenoid would be energized, right? So again, in the example of the vending machine, the rod through the solenoid would move, trip a lever, the door would open, and the person would get their soda. Now, let's see, a couple other things here. Well, notice that, again, like we mentioned before, the collector to emitter here is acting like a short. Right, because VCE is made to equal 0. That's one of the conditions, and that was based on the selection of RB, the value of RB. And even though there's 0 volts across the collector to emitter, there's a current flowing, this 100 milliamps. So that's why we say that the collector to emitter is acting like a short, because it has the same voltage current relationship that a short does. Now, the last thing here that I want to point out, and this is why it's called a driver, is that, look, we're still getting current gain here, because there's your collector current, there's your base current, right? Remember, beta, the current gain, is just the ratio of collector current to base current. So 100 milliamps divided by half a milliamp, that's a beta of 200, right? That the collector current's 200 times greater than the base current. So you see, you can get an appreciable current gain. Now, it's not equal to the optimum, which is beta spec, but that's expected because we're not in the active region. Remember, when you're operating a BJT as a switch, and when the switch is on, okay, namely when you have base and collector current, that's when the BJT switches on, it's saturated. Okay, so you're not going to get the optimum current gain, but you can still get an appreciable current gain. So it's important to understand that even when you use a BJT as a switch, you can achieve current gain. And the reason why this circuit's called a driver is because often the input voltage of a circuit like this is coming from some digital type of circuit, some circuit maybe in a computer. And those circuits don't have a lot of current capability. They don't have enough current to directly drive a solenoid, which often needs, as in this example, hundreds if not more milliamps in order to be energized. So the computer circuitry can't provide the current that the solenoid needs to energize directly, but by using a transistor, a BJT, that has that current amplification capability, we can still control the solenoid being on and off, and when it's on, the transistor can provide the necessary amplification and current to actually energize the solenoid. So that's where the name driver comes from. Okay, it's just the ability to use the transistor as a switch, but also provide current gain to drive or operate some device that otherwise couldn't be operated directly by some other lower current capability circuit like a digital logic circuit.